This is Unit 5, Section 5.2, Discrete and Continuous Variables, Day 2. And so we're going to continue our discussion on discrete and introduce continuous. So this is our second day in our unit as we continue looking at random variables. And so to recall from day 1, we looked at discrete random variables, or random variables with a finite number of possible outcomes. Expected value has a formula, so does standard deviation. And I misspoke on my last video where I said that it wasn't on the formula sheet, but I was looking up at descriptive, not at our probability distribution. For any discrete random variable x, here's our average, here's our standard deviation. And again, we can do this one typically by hand, but anytime it asks me for a standard deviation, I'm going to use my calculator, and we'll review that process again today. Revisiting this idea of the roulette table, we have a continuation. It says the new bet, red, black, and the corner bet we discussed before in roulette both have the same expected value. So we calculated the expected value here that we would lose a nickel for every dollar bet we made. So how do you think their standard deviations compare? So if we found their standard deviations, could we compare them to confirm our answer and then use our calculator to calculate the mean and standard deviations? All right, so we have been told that these have the same expected, and we're thinking, okay, what about their standard deviations? This red-black model, if you look at our roulette table, there's an even number of red and black, and then there's 2 greens here. And so when we take our 38 total and subtract the 2 and then divide by 2, there's 18 red and 18 black with 2 green. And so when we think of our probability table, the payout for this one, when we win or when we lose, okay, when we win, we get our dollar back plus $1. When we lose our dollar. So in order to win on the red-black model, we have 18 out of the 38 places we can win. When we lose, that means there's 20 out of the 38 here. That's a little different from the model that we did on the corner bet. That was we could win $8 or lose our dollar, but this happened 4 out of the 38 times, and this happened 34 out of the 38 times. And so if we want to compare their variations, they have the same idea. It's a dollar bet, we could lose $1. So if they have the same expected value here, why are the payoffs so different here? So let's look at our calculator and see what the expected values are and standard deviations. So I'm going to grab my calculator here, and I went to look at our corner model again using the calculator. So I edited, and then list 1, I put this one first. So we could lose our dollar 80.89474% of the time, or a proportion of the time, and 8 is what we would win, and that's about 11% of the time. So if then I go to stat, calculate, one variable stats, associating list 1 with list 2, this is my frequency list, and calculate. This confirms our nickel loss here, negative 0.05, and if we look down here, here's our standard deviation, 2.76. So on average, the corner bet is going to lose a nickel, but it can vary by $2.76. So on either side, it will have some variation on this, where we could lose more, but we also stand to gain more. So let's look at this game. So if we look at the bet that says, okay, I'm just going to pick a color. I'm going to pick either reds or blacks. They have the same probability table. So I'm going to edit this to where I could win $1 or I could lose $1. Oop, wrong list here. Win $1 or lose $1. And then I put a negative instead. It didn't like it. Let's do -1 here. And then we said the probabilities associated with winning. Here we have 18 possibilities for red or black out of the 38 total. So it'll find our probability there. And then to lose, we have 20 options that would lose out of 38 if they were the opposite color of the green ones. And so if I go to stat, calculate one variable stats where I have list 1 as my random variable and my probabilities in list 2. And again, this confirms that losing a nickel, so they do have the same expected value, but then here as we look at our standard deviation, we have 0.998. So I'm going to say just 0.999 here. And so if we kind of look at this idea, they have the same expected variables, or the expected values here, but their variations are different. And so this is why the payouts are different here. This one, it's more of a risk, okay, but better payout. You have the possibility of winning more here, where this one, you could play this pretty frequently and you're still going to be expected to lose the same amount, but it's not going to vary as much because we're going to get that less risk, but also less payoff. And so again, there's lots of different bets you can make. If you look at this table here, this is just the bet and odds table for any roulette value. And so if we wanted to bet on 0, there's only one place you can win, 35 to 1. So if you bet $1, you would lose your $1 or you could gain $35. And so as you look at that, we would have all these opportunities to kind of look at this here. Keep in mind that we have the European board versus the American board. So kind of see that expected value. Notice here, they already have those lose a nickel, lose a nickel, lose a nickel, lose a nickel. So they're already counting on that. Doing a top line or basket, okay, where you just do the 0, 0 and the 1, 2, 3, that even is a riskier bet, but the payoff is pretty good. It's a 6 to 1 payoff here. Then we still have losing a nickel, losing a nickel, losing a nickel for most of the bets here. So kind of keep that in mind that there's this idea of the risk associated with each game. All right, so as we keep looking here, we're going to introduce our continuous random variable, and this is a random variable with an infinite number of possible outcomes that lie within a range of values and is described by a density curve. Excuse me, had to sneeze there. Good grief. All right, so this is going to go back to our normal distributions where we can do normal calculations. So for example, it says the heights of young women closely follow the normal distribution with a mean of 64 inches and a standard deviation of 2.7. Or we could write that using our normal description, 64, 2.7. Now choose one young woman at random and call her height y. Okay, so they're defining this random variable as y. If we repeat this random choice very many times, so over and over and over again, the distribution of values of y is the same normal distribution that describes the heights of all women. This is probability. It's getting into that idea that once we do it over and over and over and over and over again, we're getting to about the same normal distribution of the population. Find the probability that a randomly chosen young woman is between 68 and 70 inches tall. So we're asking for this probability that says, okay, what's the probability that it's between 68 and 70 here? So on average, they're at 64, and it can vary by, let me get that, 64, but it can vary by 2.7. So we would go up 2.7, so 64 plus 2.7, 36.7, whoop, 66.7, And if we did 67, 66.7 plus 2.7, good grief, better check my math here. We get 69.4 plus another 2.7, we get 72.1. And going down the other side, we can subtract 2.7 to get 61.3, subtract again to get 58.6, and one more time to get our bottom 55.9. And so we're interested in 68 to 70. Okay, so 68 would be somewhere around here, and 70 would be somewhere over here. So we're looking for this probability. And so when we find this, because it's approximately normal, we don't have a table of distributions here like we did for a discrete random variable. We can go back to our normal calculations. So we can do a normal CDF with a lower bound of 68, with an upper bound of 70, with our mean of 64 and our standard deviation of 2.7, we can find this probability. So if I go to my calculator and I'm going to go second distribution, option 2 for normal CDF, I'm going to go lower bound of 68 up to 70 as my upper bound, centered at 64 with a standard deviation of 2.7. Paste that in, or use commas here as we enter it in, and then we get a probability of 0.0562. And so find the probability that a randomly chosen woman is between 68 and 70. There's about a 6% chance that we would choose a random woman and her height be between those two measurements. This should be feeling more like a review. Even though we're calling this a new idea, we had a quantitative variable that we could approximately normal distribution, use normal calculations to find proportions, percents. Now we're adding in that idea of probability and calling it a continuous random variable. So there is a difference between the idea of continuous and discrete. So if we have a continuous random variable, how is the probability of x, some random variable, less than a related to the probability of x less than or equal to a? These two, they are the same. And so if I think of a distribution that's centered here with a normal approximation, and say I was interested in this observation and below, so some a here, whether or not this is a dashed line or a solid line, it doesn't matter the area. There's no area to this line or to this line here. So if I have a greater than, or I'm sorry, less than or equal to, or just less than, those are going to be the exact same value. When we do a discrete random variable, the probability of x being less than a relating to x less than or equal to, they are different. Okay, when I have a table, like when we were talking about the APGAR scores, 1, 2, 3, 4, 5, 6, 7, 8, if I said the probability of x less than 3 compared to the probability of x less than or equal to 3, now this is a difference between less than 3 here and less than or equal to 3 here. So for this one, I would be adding up 4 values. And for this one, I would only be adding up those 3 values here. Those are different ideas because it jumps from one to the very next observation. These are not in between values that are possible on the APGAR score. You're either a 2 or a 3. You can't be a 2.5 or a 2.99999999999. It has to go to the next one. Here, a or less than a is literally the difference between a line and a dashed line. There's no area difference there in a continuous random variable. So be careful reading those tables. The signs matter here. And as we continue in this unit, we'll see that as well. All right, so let's look at another example here. It says the weights of 3-year-old females closely follow a normal distribution. The weights of 3-year-old females follow a normal distribution with a mean of 30.7 pounds and a standard deviation of 3.6 pounds. All right, normal distribution. Woohoo! Randomly choose one 3-year-old female and call her weight X. Okay, so we have defined our random variable as X. Find the probability that the randomly selected 3-year-old weighs at least 30 pounds. Okay, so the probability that X, our weight, is greater than or equal to 30 pounds. All right, so this is going to be normal CDF. We have a normal calculation. I'm looking for a probability. Tells me normal CDF. Lower bound, I'm going to say 30. Going to infinity as my upper bound. Centered at our mean of 30.7 and our standard deviation of 3.6. So when I put this in my calculator, I can get a probability of 0.577. So there's a 57% chance that I pick any 3-year-old female and she would have a weight that is more than 30 pounds. All right, on part B, find the probability that a randomly selected 3-year-old female weighs between 25 and 35. So now I'm going to have my lower bound 25, and then I have upper bound 35. And even if I changed this and I said, oh, between, so not equal to, just in between, it wouldn't change my calculations. It's a continuous random variable. A female 3-year-old can weigh 30.1, 30.2, depending on the precision of our instrument that's measuring her weight. So we would do normal CDF. Now we'd have a lower bound of 25, an upper bound of 35, and same mean and standard deviation. Look on my 3. All right. When I enter this into my calculator, I get 0.827. Again, it tells me find the probability, tells me to do normal CDF. So there is an 83% chance of me picking a randomly chosen 3-year-old and her weight being between 25 and 35 pounds. On part C, it says if the probability of the weight here is less than K is equal to 80%, find the value of K. All right, so now we're looking for an observation. We're trying to find a weight here. This is where we're going to change gears, and we're no longer doing normal CDF. We're going to be doing inverse norm. All right, so on our distribution, we have centered at 30.7, standard deviation going down, of 3.6 pounds here. We have some observation K that when we have it here, it is less than that value is 80%. So here's 50%, here's 84%, so K has to be somewhere here. And so I'm using empirical rules, so that tells me 50% in the middle, 68 here. So 50 plus 34. There's some observation that all the weights less than this observation equals 80%, 0.8. So Beyonce's happy with that 0.8, and then I have my mean and standard deviation to help me calculate this. So here's my area, here's my mean, here's my standard deviation. And when I calculate that for my K value, I get 33.7 pounds. And so this is where we would have some value here, 33.7, that says, okay, what's the proportion, what's the probability, what's the percent of observations of weights that are less than 33.7 would be 80%. So that kind of checks off our conclusion there. And again, this should be more of a review from Unit 3, where our new part here is really our discrete random variable. Knowing that those two have different calculations and that a discrete random variable typically gives you a table, a continuous random variable will give you a normal approximation. So the last part of our notes here are just those calculator steps here, so making sure that we know how to use our calculator if we get stuck, and so you have something to reference on your own. Let me know if you have any questions, and we'll keep working on random variables.